Morning, people. I hope you're doing well, my lovelies. So let me show you something pretty. It may even contain science. Cool science. Hey, it's summer in my hemisphere. I think about these things. Though my town endured a hurricane recently, our more typical August weather pattern involves heat. A lot of it. Enough that even as Angelinos try to keep cool, we also try to avoid overloading our power grid as we all simultaneously reach for the air conditioning. Now, a lot of things can make a building more or less livable during summer. Lots of places here never invested in insulation in our walls because, hey, our weather's perfect and will always be perfect, right? So, contractors save themselves the cost, but scientists and engineers are always on the hunt for new ways to make our buildings cooler, so we don't have to crank the AC quite so high. And one big way is to paint your building to be more cool. Not like aesthetically, though we'll get to that, but using paint with higher reflectance to take heat and return to sender rather than accept that package and burn fuel to counter it with AC. The most obvious way is to leverage principles I learned in elementary school art class. Paint your building, especially your roof, white. White reflects light and is the best color for reflecting suboptical EM frequencies as well, like thermal infrared. It's nothing fancy, and conventional white paint from the hardware store reflects anywhere from 80 to 90% of light, which is a lot of power saved. Thanks to physics. Thanks, physics. White is always going to reflect light pretty decently, but that doesn't mean all white paint is created equal. We've previously covered developments in ultra-white paint invented specifically for use in cool roofs like these. And that ultra-white has reflectance of 98%. Each 1% of increase in reflectance translates to 10 watts per meter squared worth of cooling per hour. So where hardware store paint saves 70 to 80 watt hours per meter squared every day compared to unpainted controls, ultra-white saves over 80 watt hours per meter squared per day. How does ultra-white get its edge over hardware store paint? Materials. Paints are made of a pigment, giving it its color, a binding agent to get the paint to adhere to the surfaces painted on, a liquid that holds these materials in suspension, and typically some extra additives to adjust viscosity, hardness once it's painted on there, or bubbliness, a quality that's lovely in a person, but suboptimal in a paint. Ultra-white paints are definitely white. No eggshell here, but pigment isn't the difference maker between hardware store and publishable engineering breakthrough. A lot of it is other stuff. Ultra-white has a ton of variably sized particles suspended in it to bounce sunlight, and one of the big tricks in cool roof paint is maximizing your cooling components. In ultra-white's case, barium sulfate makes it both super reflective and super white, without losing the qualities that make it good paint. You want it to be super reflective, but you also gotta be able to put some pigment on the surface, and it's gotta stick. Engineering, as always, is about trade-offs. But as good as it is for our energy bill, everything all white all the time is kind of boring. I don't want the world to look like an Apple store. Paint isn't the only way to get a cool roof. Green roofs full of plants are also empirically tested to be cool as heck. But within the low emissivity or high reflectance paint category, you're mostly looking at white, metallic, gray, paints that are optimizing the cooling component concentration at the expense maybe of looking cool. So we were overdue for this latest cooling paint technology brought to you in an article in the Proceedings of the National Academy of Sciences. And that article pretty much asks, what if color. After all, we just said that the big difference maker between hardware store and fancy research paint is in the additives, and there's nothing that says a dog can't play basketball, and there's nothing that says you can't put those additives in with fuchsia pigment. This new cool paint formulation is a bilayer setup. The top layer has pigmented nanoparticles designed to be as transparent to infrared as possible, while the bottom layer is full of aluminum flakes to bounce and reflect the light away from my poor broiling apartment. So, when light hits your building, it passes through the nanoparticle pigment layer, gets bounced by the reflective layer, passes back through the nanoparticle layer, and right back that infrared goes to the world, stopping me from reaching for my thermostat. Energy saved. These colorful cool paints are at their strongest when reflecting mid-infrared light. Their reflectance in that range is 80%. Now, that sounds pretty bad when we compared to ultra-white earlier. That's 80%. Wasn't that basically commercial white paint reflectance? And each 1% reflectance is 10 watts per meter squared per hour? Yes, but those two numbers aren't quite measuring the same thing. Ultra-white's 98% reflectance is total solar reflectance, which includes visible light, and obviously white is going to reflect that better than any color paint can. But visible light isn't what's got me wearing an ice pack in the summer. It's infrared, and that's where this new paint is winning out over its commercial counterparts. Commercial paint reflects as little as 10% of mid-infrared light, so the 80% reflected by cool, pretty colors is a tremendous improvement. And because we're not worried about the visible spectrum, these results work for dark colors like they do for lighter ones, even if not to the same extent. You can see that dark gray BLC on the bottom graph, that's bilayer coating for our test paint, is keeping right up on our other colors. And though additional, deliberately darker shades in the study didn't quite match up to our brights here, they still very comfortably outperformed commercial paint. After all, our fuchsia doesn't have to be cooler than ultra-white, it just has to be cooler than the store-bought fuchsia we have now. This paint isn't totally groundbreaking in its field. Bilayer paints with metal flakes in them have been a staple of cool paint research for years. In fact, one of the reasons our previous ultra-white was such a big deal isn't just that it's so freaking white, though it's so freaking white, but rather it's that one layer, simple to apply, it makes for a good, usable paint. Look, I can't even reliably paint my walls evenly with normal paint, so the bilayer setup of this new paint is a bit more finicky by comparison, but as cool paint technologies mature, more factors come into consideration. Weatherizing, ease of manufacture, price of components, and at the risk of being obvious, color is a big component of being a good, usable paint. Without cracking the color question, cool paints would be relegated to utilitarian use cases only, where you don't really mind if everything is gray and white. This research is so exciting because it brings energy-saving paint that much closer to real-world, widespread adoption, and it looks good while doing it. Look it! It's pretty! I did the yellow. Or maybe the blue.